For the syllabus, inorganic chemistry, chemistry 216, again, Heracus. Whether you mispronounce my name or not, really not a big deal. I'm most likely mispronouncing my own name because I'm not from the Mediterranean with a thick accent like my parents. Heracus, same thing. So you should have this textbook, Inorganic Chemistry, Housecroft and Sharp. This one's the 4th edition. They also have the 5th edition. Either one is fine. So it's essentially the same book. A few things change and so forth. I'll talk more about the textbook once we get to kind of the material. My office is in Center for Sciences, 3rd floor, 373. So for office hours and the like, you can find me there. For this course, along with the textbook, you'll probably need a scientific calculator because we will be doing some calculations like Ka, equilibria, and so forth. I'll talk about that a little bit later. With Chemistry 216, obviously there's no lab, so it's all lecture. In this course, we're going to really draw heavily from your Chemistry 111, 112 course, especially at the beginning, Chemistry 111. Now, one of the first things you're going to find is that everything you learned in Chemistry 111, as far as chemical bonding, is a lie of omission, because there's a lot of stuff that was not covered in there. And so it's absolutely critical to go back and read through your notes from Chemistry 111 and 112. It's also incredibly important to be on time. For this course, as we go forward, the very beginning is going to seem like review, because it is, of going through some of the material from Chemistry 111. If you haven't done so, has everybody seen the Quiz 0? I was pestering you all, sending that out early in the summer. You should go through that as if it's an exam and have a periodic table and maybe a calculator and nothing else, and just work through it and see where you get stuck, because like I said, that stuff will come back to haunt you a little bit later on. So as far as, again, for this course, attendance, I won't be taking roll on a regular basis, but as I said, we will have quizzes in class. And that's one of the ways I kind of encourage you to show up. I'll let you read the stuff yourself. So going to the lecture schedule. Now, the first couple chapters, chapters 1 and 2, really bleed together because it's the fundamentals of the atom, quantum mechanics, and it goes right into chemical bonding. And we're going to spend a lot of time talking about chemical bonding in various levels as we go through. Now, I will say your book can be a little bit daunting when you start reading it, because it really starts off like a physical chemistry book where it dives into some of the higher math aspects of quantum mechanics. We're going to navigate through that without going into the heavy lifting of the math. That's why you have PChem 2, in case you're wondering. So if you feel disappointed that you're not going to be doing triple integration or Hamiltonians and good stuff like that, just take PChem 2 and you'll be fine. I took a course called Quantum Spectroscopy when I was in graduate school, and it was a lie. It was just a math class. It was just literally quantum mechanics, but just Hamiltonian. So we just did Hooke's law all day long, solving math, and it was tragic. Going through the first couple chapters, again, it'll seem very familiar. Then as we get into chapter 3 with molecular symmetry, we're going to start introducing some really new concepts that you haven't seen before in Gen Chem. One of the assumptions I make is that you haven't had organic chemistry. Some of you are inorganic or have had organic, and that's fine. That basically gives you a good foundation. But if you haven't had organic, it'll be okay, because as we go through this course, we will actually draw in certain aspects of organic chemistry simply because it's a means to an end. It's needed. There's a field called organometallic chemistry, where we have organic stuff, squishy stuff, and it's attached to a metal. So we'll figure it out going from there. As we progress through the book, we'll go more or less in order, but we're not going to cover every single chapter. And in some chapters, some of the material, I'll bring in aspects of what we're talking about from other texts, whether it's a paper or another textbook or so forth. So as you are preparing for the course, I'll be sending out reading assignments and homework to try. Now with the homework, if you notice, I've got that as 5%. Typically, on the grading, I'll have a few problems that you'll do and hand in, but it won't be like the whole assignment. I'm toying with the idea of having some quizzes on D2L that will count as homework. And really, the only reason I even put the homework in is to keep you honest, in the sense of giving you a little bit of incentive to actually do some of the problems and keep up. Because it's real easy to just look at me when I'm lecturing and go, oh yeah, I understand that, but that never do the problems, and then find out that wasn't a good strategy. So again, we'll have 3 exams, some quizzes, homework, and of course a final. And I've got the syllabus on there. You can read through all the gory details of the honor code and etiquette and all that. But at this point, you've been through 111 and 112, so I'm going to assume you know everything about everything as far as how to be in a class going forward. So. Probably the biggest question is, when is our first quiz? And right now I'm thinking it'll be Friday, and which might seem very unfair, but it's going to be mostly on Chemistry 111 type of stuff. So I'm going to give you some incentive to actually remember your general chemistry, but I'll say more about that later on. So the first question, what is inorganic chemistry? A better question is, what is organic chemistry? How do we define organic in organic chemistry?
Carbon.
Carbon? Yeah. Sometimes you'll hear it referred to as the study of carbon. But why is it called organic? You go to the store and you buy some organic eggs, right? Is there an inorganic egg section?
Yes.
Because they originally thought there was like this life force that went into all carbon compounds and stuff.
Yes. So, kind of goes to the vital force idea in biology that if you want sugar, you have to get it from a plant. If you want fats and oils, you need to get it from an animal or a plant. Any type of molecule that has some, biological properties had to come from something biological. But we know that's not true. Wooler in 1828 synthesized urea from inorganic materials that basically came from minerals. So there was no plants, no animals involved. And once that synthesis was done, showing that I can take some things I dig out of the ground, some essentially minerals, compounds that have no life associated with them, and make a biological molecule, the urea that he isolated was identical from urea isolated from animals, whether it's human or dog or whatever. Right there, that proved this idea that biological molecules are special. Well, they're not. So, ironically, organic chemistry started from inorganic chemistry. Probably a better way of referring to inorganic chemistry as just chemistry. That there was no separation of organic and inorganic until basically we got here. And then physical chemistry, they go off and do their own thing because they're more on calculations and physical aspects, as the name says, and so forth. Quantum mechanics in there as well. With inorganic chemistry, inorganic basically means without life, no biology. However, what we find is that there are going to be many aspects of inorganic chemistry that actually do have a predominant importance in biology. If you think about hemoglobin, in the center of it, it has iron. right? And we'll see coenzymes and other types of things like that have metals in them that are inorganic. Another way of thinking about it is, well, you can breathe oxygen and you can have CO2 going in and out of your lungs. But what happens when you breathe in carbon monoxide?
Something different happens.
Yeah, you die. Yeah, there's, which is a problem. But why? Why is CO2 and oxygen and nitrogen, all of those molecules can go in and out of your lungs, your body, without any problem? But little molecule CO, now we got problems. Well, what's happening is the carbon monoxide really likes to bind to iron. And so what we find is the problem is that the molecule wants to stick onto the iron. Well, when that happens, it blocks your respiration. To explain any of that is going to take us a while because we're going to have to go through many aspects of chemical bonding and coordination chemistry to explain how a molecule can bind to a metal that way and going forward. So there are many aspects of, again, inorganic chemistry that will have a root in biology. On the flip side, when I worked in industry, I worked in the semiconductor industry. So silicon, gallium arsenide, compounds like that that are used for microelectronics, computer chips, and so forth. And that's another very important aspect of inorganic chemistry. So if you're talking about things like hemoglobin, that gets you into the field of bio-inorganic chemistry, which is kind of an oxymoron, but it is what it is. So, but that's not a field I'm in, because my father, he was a chemical engineer, then he became a biochemist because Monsanto needed biochemists in the 70s. And I thought I wanted to be a genetic engineer, cutting plasmids and doing all that stuff. But then senior year, when I'm taking biochemistry and the professor says you have to memorize the 20 amino acids, I had been doing lanthanide chemistry for my research. And so when he says you have to memorize the 20 amino acids, that's when I said no. Actually, I don't. I dropped the course and became an inorganic chemist, and I never looked back. It's one of those things where you as an undergraduate, you don't really know where. Like I said, I thought ironically I took all these biology classes, but I never declared a biology minor or major. I was just like taking them, and because I thought I wanted to be in that field, and so that was a complete waste of my time. Taking genetics and all that kind of stuff. But anyway, with inorganic chemistry, we're going to find that, yeah, it's going to go off into a field that's going to seem very alien, but it's here. It's, the other parts of the periodic table. If you think about your Chemistry 111, you spend a lot of time in groups 1 and 2 and 13, maybe not so much in 18, doing Lewis dot structures and so forth. And then what happens, when you get, to iron? Well, why can't you use the Lewis dot structures there? Or you have, selenium, and it's got 6 fluorines around it. Your expanded octet, right? Well, all of those things are basically saying that there's a piece of the puzzle missing as far as chemical bonding and so forth. And that's something that's going to be fundamental to inorganic and, quite frankly, to anything else that you might be interested in as far as chemistry and STEM and so forth. So that's something, again, with this course, it's really foundational. And what's different about this course than what I had when I was an undergraduate, we only had advanced inorganic, and that's the 416 course that's offered here. And that has a lab. So for me, senior year, I got 1 semester of inorganic chemistry, both lecture and lab. Where here we kind of split it out, where we've got this course and then 416, which also has a laboratory associated with it. Okay, so chapter 1 really, again, starts at the fundamentals, starts with the atom, and goes from there. And so I will do the same. Now I'm going to intentionally skip a lot of background material on quantum mechanics to kind of move us forward, because I'm not going to rehash absolutely everything from Chemistry 111. But if we're thinking of in terms of the atom, right? So we've got a nucleus. Where is the mass? right? So we've got our protons, our neutrons, and here, different colors. And relative charge, right? So a proton's going to be +1, whereas a neutron is going to be 0. And then somewhere, I'll put 2 of them to make this helium. Somewhere off in space, we've got electrons, right? Again, E- is the symbol for an electron. And this circular path that the electron is taking, what do we call that? Orbit, orbital, right? Now, we'll see this simplistic model, essentially the Bohr model, works really well, except when you have 2 electrons. It starts to fail. The idea of the electron orbiting the nucleus, conceptually, that's really great, but it's fundamentally wrong. But it's a good place to start. In fact, we still use the term orbital from orbit, from Bohr, even though that's, like I said, not a proper description. When we're looking at, again, forgot the charge, right? So relative charge, so our electron has a -1. We're going to find that to understand anything about chemistry, we're going to have to spend a lot of time understanding the nature of the electron, right? In other words, proton and neutron are pretty straightforward. They're particles with mass, but the electron, it's a charged particle, but of course it behaves like a wave, right? In other words, remember your quantum mechanics. So we're going to be going into that over and over and over again, just to get, again, some footing as far as getting back into the swing of things. So if we have just a generic element, all right, again, our periodic table, Z is the atomic number, which is the number of protons. The number of protons defines the element, right? Hydrogen is 1, helium is 2, lithium is 3, and so forth. Our A number is the mass number, and it's the protons plus the neutrons. So for hydrogen, if we have no neutrons, it would just be 1 and 1, like this. Right now I'm ignoring charge. We're making the assumption that we have 1 electron. We'll talk about that. This is also referred to as protium. But then things start going off the rails because we can have another form of hydrogen, where now instead of 0 neutrons, right, we have 1 or 2. Collectively, what are these 3 called? Hydrogen is an element, and these are the isotopes of the element, right? Hydrogen is unique in the sense that its isotopes have a unique name other than what we normally use. So we have deuterium. For protium, in some textbooks, you'll see it as H or even as P. I think that's more physics, particle physics type of things. Deuterium, again, you'll see it abbreviated as D. And then we have tritium. As T. When we observe hydrogen in nature, it's a combination of the 3 isotopes. Hydrogen is about 99%, deuterium is about 1%, and then tritium is trace, very, very small amounts. Unless you've done something to enrich it, for example, and so forth. And again, this is something that hopefully will sound very familiar. Isotopes And allotropes, and then isomers. It's very easy to get the terminology all mixed up, but we'll be going through that. So again, this situation with the boards, not perfect, but we'll do it. Molecules. Now we're taking our atoms and starting to put them together, right? And we'll have to define some of these things a little bit better, but that'll be fine. Actually. So we go from atoms to molecules. Now, with hydrogen, if we just had hydrogen as monoatomic, well, that obviously we know is going to be a problem. So we find it as diatomic. And I'll come back and we'll have a refresher on Lewis dot structures and all that good stuff. But again, this should hopefully be very, very, very basic, very familiar. With some elements, so like oxygen, we can have diatomic oxygen, or we can have triatomic oxygen. What's O3 called? Ozone. Mhm. So if you have the same element, but it has a different structure or chemical formula, those are referred to as allotropes. And by the way, sometimes the way you'll see it spelled, it'll have an H, or some textbooks leave off the H. It's fine. Or allotropy. A perfect example would be graphite versus diamond, right? In other words, two forms of carbon, but different. And again, it's real easy to get some of the terminology of isotope and allotrope confused if you haven't been paying attention to your Gen Chem since the break. Now, how do we justify all of these chemical formulas, right? Well, I have molecules, which again, which we're talking in terms of covalent bonding. But then we can also have something like salt, table salt, which now is ionic bonding. What differentiates ionic and covalent? In other words, how do I know if it's going to be charge separated or if we're going to be sharing electrons?
The difference between their charge.
Not charge, but you're on the right track. What's the term? What type of atom? But there's a specific term I'm looking for, fishing for.
Cation and anion? Charge. Electronegativity.
Electronegativity. Yeah. See, in other words, cation, anion, plus and minus. But why does it form plus and minus? And this is, again, the periodic table. This is your Rosetta Stone, your Holy Grail, your roadmap, whatever you want to call it. You need to be able to read the periodic table and understand what it's telling you. Over here, we have the metals, right? They have very low electronegativity. Let's ignore the transition metals and the lanthanides and actinides. As we get to the non-metals, electronegativity starts to increase. The way to think about electronegativity is as if it was a game of tug of war. Fluorine is going to be the strongest. Say, francium's radioactive, so we'll ignore it. Cesium would be the weakest. When they get into a game of tug of war, well, the fluorine wins and it removes the electron. It pulls it away. But if we have two elements, like or two atoms that are the same, like oxygen, when they're pulling on those electrons, well, they cancel each other out, and we end up with covalent bonding. So the difference in electronegativity is what defines if the bonding is ionic or covalent. But of course, it can be much more complicated than that, as we're going to see, because of what happens when you're very close to that difference. Now, I don't want to put any numbers in your notes right now. If you had it in Gen Chem, there's a rule of thumb where if the difference in electronegativity is 2.0 or greater, then it's ionic, and off you go. When I was in graduate school, it was really funny because there was a professor who was analytical, and he was trying to say that boron and fluorine, their electronegativity difference is a little bit more than 2, therefore it's ionic bonding. The only problem with that is it's not. You don't see the physical properties of BF3 as ionic, they're actually more covalent. And it was really funny because he was trying to make this argument in front of a room full of inorganic chemists. And it was really funny watching some of my professors, like their heads about to explode. Because if you think about sodium chloride, it's a salt, it's got a very high melting point, right? And you can dissolve it in water, it's a conductor. But BF3 at 25 degrees Celsius, 1 atmosphere, is a gas, right? It's molecular in nature. So even though I can play the electronegativity difference game, as it turns out, its bonding is better described as covalent rather than ionic. And that's something that, as we go forward in inorganic chemistry, we're going to find many examples where we look at something and say, oh, well, this should be this way. But then as we look at the actual data, it doesn't give us the result that we expect. So what we have to do is we have to dig a little deeper. We have to figure out what is going on from our chemical bonding point of view, or some other aspect of it. So like I said, right now, I don't want to dive into the specifics of it, but if you remember, we have metals, we have non-metals, right? And if you have a metal and a non-metal interact, it's going to be ionic. If you have non-metals interacting with themselves, well then now you get into covalent or what? Polar covalent bonds, right? So this same professor is really funny. So he was, I was a graduate student at the time, and I made the mistake of actually sitting in his lecture one time because one of my classes was got, and he was trying to explain polar and non-polar, and so he did this. He drew H2 and said, it's non-polar. But how does that mean anything to the freshmen? You have to do this, right? You have to show. All right, so if this is a game of tug of war, if each of these have the same electronegativity, I believe it's about 2.1. So if this is pulling in that direction, 2.1, and this is pulling in that direction at 2.1, what's the net? 0, right? There's an obscure field called physics where they would say this is vector math or something like that. I don't know, but yes, it's a game of tug of war. If you have identical twins, nobody's going to win. Non-polar, pure covalent bond. But if you have this situation, hydrogen with bromine, and I'm going to get all fancy electrons on here. Who has the higher electronegativity? We'd assume it's going to be bromine. I chose one that's not perfectly cut and dry, because as you move down the column, what happens? Electronegativity
goes down. It
goes down, right? So without looking at the numbers, we can make the assumption that bromine is more electronegative than hydrogen. By how much more, we don't know. Again, without looking up the number. But if the difference, regardless of which direction, if the difference is non-zero, in this case, we get a polar covalent bond. Based on, again, electronegativity difference. And I know I'm zipping through this stuff, but we're gonna code through this in a more formal way. But right now, I'll just kind of push you into the deep end, just to get you guys thinking about what you should know already. If your electronegativity difference is really great, like in the case of sodium and chlorine, instead of sharing the electrons, your game of tug of war, well, somebody loses badly. In other words, the electron is transferred from the sodium to the chlorine. That's how we get ionic bonding, right? But we're going to find that there are going to be many aspects of understanding the nature of the chemical bond that we're going to have to go a little bit more in depth than just electronegativity and some of our Lewis dot structures and so forth. If we think about Lewis dot structure, the octet rule, what does that mean again? Octet.
That's the maximum number of valence electrons allowed.
Hmm? And octet would be 8. Why is it 8?
Because nature says so.
Hmm? Why? Give me.
I guess the group 18 on the periodic table has 8 valence electrons.
Hmm? But depends on which element. I mean, helium doesn't. See, that's where you have to be really careful because, yeah, you can get yourself into trouble when you're looking at the periodic table and the first element in every column usually screws you up. 8, we're going to see, comes from our s orbital, px, py, pz. Remember, we have those orbitals, right? What we're going to find is something like the octet rule, which you probably even saw in general chemistry, and then you saw hopefully again in 111. It's really useful until it completely falls apart. And the reason it's going to fall apart is, well, groups 1 and 2, those are what? Those are our s orbitals, 13 through 18, ignoring helium. Those are our p. But then we've got the d orbitals to deal with. And the f orbitals, fortunately, they don't really participate in bonding. So what we're going to find is, as we start looking at certain aspects of chemical bonding, something as simple as the octet rule, which is really, really good, fails miserably from time to time, more often than not. Does anybody know the time frame of when Lewis dot structures, G.N. Lewis, Gilbert Lewis, about the time frame of when he published Lewis dot structures? I'll give you a hint. Well, I'll give you a point of reference. Schrodinger did his work of quantum mechanics in the 1930s-ish, 20s to 30s.
50s, 60s.
So Gilbert Lewis, the first paper I've seen of him talk about Lewis dot structures was like 1905. So he was like 20 years ahead of modern quantum mechanics for chemical bonding. So the thing that we use as chemists on a daily basis of explaining chemical bonding actually predates the more rigorous method of chemical bonding. So Lewis actually developed his form of chemical bonding before an s orbital or a p orbital or any of that stuff was defined. There wasn't even the term orbital at this point, but he did it all empirically. And that's something we always have to keep in the back of our mind because we go to Lewis dot structures all the time and they're not always correct in what they're telling us. So we have to, like I said, have to be careful about that. And that's something that as we go through these first couple chapters, we'll be revisiting that. And I can give you a couple examples of why we have to essentially abandon Lewis dot structures. Now, we're not abandoning quantum mechanics, just the opposite. We're going to be diving into it with reckless abandon. BH3 is an inorganic compound called borane. But borane, and this would be in the gas phase, borane is only observed in the gas phase using spectroscopy. Experimentally, what is observed is the dimer, where it's B2H6, or diborane. Which, okay, fine, they can come together. But here's the problem. when we have the structure of this compound, the dash is stereochemistry. So it means it's going into the back of the board. The wedge means it's coming to the front. In this case, if you don't have the stereochemistry, it's not the end of the world. Okay, so those are 4 of our hydrogens. And then the other 2 hydrogens are there. I could draw that with solid lines. In some textbooks, you'll see it with a curved line or a dotted line. Your book uses solid lines, so that's why I'm using it. What's wrong with this structure?
Hydrogen can't have 2 bonds. Or shouldn't.
Right. In general chemistry, I would dock you a bazillion points because you've got a hydrogen and it's bound to 2 borons, right? But that's the correct structure of having these bridging hydrogens. There's nothing wrong with this structure. What's wrong is, again, the octet rule and our understanding of chemical bonds. So we're going to have to swing back around to explain observations like that because, well, that's the correct structure, even though our Chemistry 111 version of chemical bonding says, well, hydrogen can only have 1 bond. That's not true. In fact, there are many examples of where you can have a hydrogen and it's bridging multiple atoms, which, again, how does that make sense? And fundamentally, we're going to have to go all the way back to the beginning of quantum mechanics of defining the nature of how electrons behave, their wave properties. But again, from a perspective of what you've been taught in Gen Chem and kind of the history of how chemistry evolved, Lewis structures started in like 1905, probably plus or minus a few years. Actually, I'm certain a little bit before that. And that kind of laid the groundwork. And in organic chemistry, Lewis dot structures work fantastic most of the time. But then it became obvious that there has to be more than just the octet rule. And something like borane and diborane really show, well, something's wrong because the hydrogen can't do that, can it? Yeah. Now, I am not going to go all the way through of reviewing every aspect of quantum mechanics. What I do plan on doing is, you have your textbook, but there's actually a open source general chemistry textbook, the one we use for Chemistry 111 and 112. I'll send you some reading from that you should use basically as a refresher, because again, ultraviolet catastrophe is ultraviolet catastrophe whether you read it in one book or another. And it's really something that, for us, quantum mechanics is a means to an end. I don't care about black holes. I don't care about their event horizon or any of that, which is, you can explain using quantum mechanics if you're Stephen Hawking and so forth. But quantum mechanics gives us the toolbox that we need to understand chemical bonding and to predict what's going to happen and explain chemical interactions and so forth. So it's absolutely critical. Just a quick reminder, right? Quanta, from quantum mechanic, what does that mean?
To count, or like number, something like that.
Nope. So let's take a step backwards. So classical physics or Newtonian physics, if I want to shoot a cannonball at somebody, I just need to know a few things and I can graph everything out. And regardless of what my scale is, let's say that's energy, and we can call that time or distance or whatever, every point on that line is defined. And so if I shoot my cannonball from when it leaves the cannon till when it hits, every single point is known, is measurable. In quantum mechanics, energy, so in here, we would say energy is continuous. But in quantum mechanics, what Planck did to explain black-body radiation is he made a fundamental break in how we view energy. Instead of saying every point from 0 to infinity is allowed, we have levels of energy where we can go from energy level 1 to 2, or 1 to 3, or 4, 5 to 2, and the energy is transferred in packets. And that's what quantum means. It means basically a little packet, a little amount of something. So packets of energy.
Photons.
Sorry?
Photons, right?
Yes, and that's the same, exactly. In other words, photon is referring to the packet of energy when it's referred to in light. Exactly. In fact, what Planck did as far as kind of this framework of quantum mechanics, and again, I don't dive into the history. You get Professor Führer, he can give you all the ad nauseum history of it. Planck apparently didn't like his own solution, because what he was doing is he had a mathematical solution for something, but he didn't know the actual theory of what was really going on. So this mathematically worked, but at the time he didn't like it. Einstein later, with the explanation of the photoelectric effect, showed that the same idea of transferring energy in packets is how you can explain the photoelectric effect. Photoelectric effect is basically solar cells. So light hits a material, it creates an electron from the change in energy. So in quantum mechanics, energy is discontinuous. The reason why that's so fundamental is because physicists had made the assumption that if you have the equations, the physics of Jupiter, or a grain of sand, or an electron, well, it's all the same thing, right? So your physics should not be changing. But what we find is, as you get to the subatomic world, as you get to things very, very small, or in some cases very, very big, you don't see classical mechanics being able to explain what's going on. This idea of jumping in levels, right? Well, these are going to be our orbitals of energy for our electron and so forth. So again, I'm not going to go through all the experiments that get us to Schrodinger. Now again, Lewis dot structures don't use any of this. In other words, Lewis, in his explanation of chemical bonding, he was doing what's called empirical science. He observed something, and then he used that to explain things. But he didn't have the theory of why. And that's why you have many instances where Lewis dot structures just don't work. How many of you remember what resonance structures are? Right? Or in organic chemistry, they call them aromatic, where you have like the delocalized electrons. Well, a resonance structure is simply saying your Lewis dot structure has failed. In other words, it doesn't work. So you draw little dots in it and you just hope for the best. What that basically says is you need a new theory. Okay, so Schrodinger. Hopefully these names sound familiar. I haven't seen the movie Oppenheimer. I think Schrodinger was actually one of the physicists in it. So it was really funny because I didn't even realize. So I think apparently Niels Bohr was actually helping out on the Manhattan Project, but under a pseudonym. He basically just was just some dude who just happened to be one of the experts in quantum physics. Just but he didn't want the Nazis to know where he was. With Schrodinger, what we're going to do is we're going to take the electron. Now, think about an electron. It has a negative charge, and it has a non-zero mass. Okay? Well, if you have charge and you have mass, that means you are not electromagnetic radiation. You're not light. Light, it behaves as a wave. But what Schrodinger's doing is he's going to take the electron and he's going to model its behavior purely as a wave. And that's one of the things with quantum mechanics that we're going to see, the idea between matter and energy, particle and wave properties, that we have to reconcile all of that. Now, obviously, I'm skipping a few steps. Now, an obvious question is, why do this in the first place? The Bohr model of the hydrogen atom is absolutely fantastic. So we have our one electron, and it's orbiting the proton, and you can actually do all kinds of calculations and so forth. But the problem with the Bohr model of the hydrogen atom is if you try and use this model with two or more electrons, it fails. Well, that's kind of a problem because once you get to helium, lithium, and so forth, well, you start having a lot of electrons. In Bohr's model, he was treating the electron as a particle. When the electron's all by itself, you can get away with that. But when you have two or more electrons, they actually interact in a wave type of behavior. Bohr had no way of reconciling that, so that's why his model failed. Schrodinger started off with the assumption that the electron has wave properties, and then everything that he was going to do, from a mathematical point of view, was to do it that way. Now, the thing is, he wasn't actually inventing this mathematics. The mathematics of how do you determine the intensity of light in a region of space. That's basically something that was already worked out in physics, and he was essentially adapting that to the model of the electron. With Schrodinger, we're not going to find where an electron is in an orbital. We're going to find a region of space where we can define a probability of finding it. So that's going to get us into something more fundamental. The very, very last thing I'll hit you with, as a refresher, wave math. Right? I'll start here on Wednesday. Give you something to think about. So what's going to happen if we add two waves and they are in phase? Constructive interference, right? And then we'll have deconstructive interference and go from there. So this is a good place to stop because we'll be opening up a whole can of worms on Wednesday. If you have not done so, go through, look at that quiz 0. I posted part of the answer key to it. Start reading through chapters 1 and 2. We're going to start the quantum numbers, electron configurations, and off we go into chemical bonding from there. So chapters 1 and 2. All right.
Thank you, Dr. Marcus.
Welcome back.
Thank you. Did you say our first quiz is going to be on Friday?
Probably.
And it'll be going over a lot of the Gen Chem stuff?
Yes, this kind of stuff. So basically, we'll see how far we get on Wednesday.
Okay. That wasn't so bad.
I might have some more days to go back and review the stuff that I don't remember.
Yeah.
So I'll probably be doing that for the next couple of nights as well as the echem homework.
That's good. Yeah, and then we have analytical. We'll see how analytical goes.